Hopefully now you understand what the regions of a Venn diagram represent, the potentially empty intersections, differences, and complements among sets. The diagrams initially don't represent any information about the set's memberships until certain changes are made. Instead, they prepare us to organize information we could potentially get about elements of our universal discourse when we do get it. The kind of information we're interested for categorical arguments can be thought of as answers to yes-no questions. For any given region, we just want to know, is there anything there? If the answer is yes, we're going to put a small x completely inside the region. That means there's at least one thing there. Meanwhile, if the answer is no, meaning the region is empty, then we shade that region. Remember that if any region of a Venn diagram is blank, that doesn't mean it's empty, but it also doesn't mean that there's anything there. For blank regions, the question, is there anything there, has not been answered and should be treated as undetermined. Using that system, there are 8 pieces of information that we could potentially incorporate into a Venn diagram for 2 sets. And it turns out that some of these correspond to the traditional categorical statements. But forget I told you that for now. Let's decide on our sets, and let's use sets of somewhat mysterious membership again. This time, I want to use vampires and demons. Now, suppose I shade this region, region 1. Think of a way to express the information that would represent without referring to the diagram. Refer instead to vampires and demons. And remember that region 1 represents the set we previously noted was V minus D, vampires minus demons. That is to say, vampires that are not demons. So maybe you come up with something like, there are no vampires that aren't demons. Or maybe only demons even could be vampires. Or how about, if there are any vampires, all of them are demons. In fact, this diagram can be associated with the A statement, all vampires are demons. People often struggle with this association for a couple of reasons. One seems to be that the A statement is affirmative, but shading indicates that something is not there, which seems like a negative, at least when you put it that way. However, affirmativeness as concerns categorical statements is really just a grammatical distinction. What I mean is there's nothing affirmative about the information conveyed by any statement or any other statement. And at the same time, the A statement, all vampires are demons, surely does tell us that something does not exist. Vampires that are not demons. So when you first think about the A statement, you tend to focus on the wrong part of the diagram. Here, this is the region where those demonic vampires go, right? But you should be focusing your attention out here because the statement is giving you information about that area, that it's empty. To help this sink in, notice how if we imagine the shaded area disappearing, the Venn diagram comes to resemble the Euler diagram for this subset relationship. Actually, there's some room for debate about whether a diagram like this completely represents an A statement. The problem concerns what philosophers call existential import. Existential import means that a statement implies, as part of its meaning, that members of the categories involved exist. So it's uncontroversial that I statements and O statements have existential import. But there is some disagreement about whether A and E statements do too. Aristotle thought that they did, whereas the 19th century mathematician and logician George Boole is commonly associated with the opposite view. To see the controversy, consider the statement M. All vampire movies are bloody movies. Now intuitively, does it seem like this statement means that vampire movies exist? You're probably thinking, yes. That's the natural instinctual response, I think. But there are some difficulties with that. Consider a different question about statements like the following, V and N. All vampires are blood drinkers. Vampires are non-existent mythical creatures. This time the question is, are those statements true? And here the intuitive response seems to be that they are. One asserts a definitional truth about them, and the other one asserts what is materially true, that they aren't real. But if we say that A statements have existential import, then both of these statements have as part of their meaning that vampires exist, even though one of them directly states that they don't. And since vampires don't exist, these statements, by implying otherwise, would have to be called false. Although we said intuitively they should be true. The Aristotelian resolution to this problem is to conclude that some A statements have existential import, whereas others don't. So M does, but V and N don't. Arguably, this gets weird. What's the difference between those statements? They seem to have the same grammatical structure. They seem to have the same logical structure. How would you know whether a categorical statement that you are making means that the sets in question have existing members? The Aristotelian can say that if and only if the sets actually do have members, then the statement has existential import, whether you know they have members or not. But then, what if we turn out to be wrong about vampires, for example? Then we're also wrong about what our statements mean. On the other hand, Booleans treat all A statements equally, which they claim is an advantage of their approach. They equate V with the statement, if there are any vampires, then all of them are blood drinkers. And they also equate M with, if there are any vampire movies, then all of them are bloody movies. According to the Boolean, we can explain why it seemed natural to say that M implied that vampire movies existed. It's just that everybody knows vampire movies do exist. So when a statement like M is involved in any sort of situation or question, we assume that that knowledge is part of the equation. So it doesn't really come from the A statement being said, it comes from our sort of background knowledge about the situation. The Boolean understanding of A statements is simpler, and it's also more applicable to topics you might encounter in future studies. So I'm going to adopt the Boolean approach for purposes of our class. The book says to learn both, but you can skip the sections related to the Aristotelian approach. So to sum up, any standard A statement can be represented in a Venn diagram by shading the region corresponding to the subject set minus the predicate set. Now, if we're dealing with a situation where the subject is on the left and the predicate is on the right, like this, the diagram's always going to look just like this, no matter what the A statement is. It takes a lot of explaining to understand why, but the procedure is very simple. Just think every time, subject minus predicate, find that area and shade it. The rest of the standard statement types are much easier to connect with appropriate Venn diagrams. Let's turn to that now. Let me give you some diagrams and ask, how would you express this information by talking about the same two categories, vampires and demons, without making reference to the diagram? Here's one in which the intersection has been shaded. You may have come up with something like, there are no vampires that are demons. It's pretty easy to see that this is the same information expressed by the E statement, no vampires are demons. And one in which the same intersection is marked with an X. If you remember that X means there's at least one thing there, maybe you come up with there's at least one vampire that's also a demon. We associate this diagram with the I statement, some vampires are demons. Now, you might be wary about whether that completely makes sense. Maybe you're bothered by the word some. Usually if I say some vampires, you think of more than one. However, when it comes to deductive logical relationships, we're interested in the minimal information content to which a statement commits someone. And I can say some are if I just know that at least one is. A more realistic example might help to illustrate. Suppose somebody asked me if dogs can ride skateboards. Now, I've only seen one dog riding a skateboard in a YouTube video, but I think I could say some dogs can ride skateboards based on knowing that one can. Granted, maybe it would be more helpful if I said, I know of one that can. Nevertheless, I'm not speaking falsely if I say that some can. If it turns out that's the only one, you wouldn't tell me, you were wrong. You said some dogs could ride skateboards, but only one can. So we'll be interpreting some as at least one. Next, let's put the X over here in region 1. In terms of sets, this is V minus D. So you might most naturally express this information by saying there's at least one vampire that's not a demon. At this point, it's probably obvious that this diagram should be associated with the O statement. Some vampires are not demons. I want to point out another confusion now, the confusion between the O statement and the I statement. Sometimes people interpret them in the same way, but they aren't the same. What I mean is, if I tell you that some vampires are demons, you might conclude based on my statement that some are and some aren't. However, strictly speaking, I did not say that any were not. Maybe I just know that at least one vampire is a demon, and it's possible that they all are. Granted, you might expect me to provide more information. If I know that they're all demons, I should say so. And if I'm not sure, maybe I should tell you that. But that doesn't make my statement false. We're interested in what would make the statement true or false right now, not whether it's the right thing to say. So when we deal with some vampires are demons, it doesn't mean that some are and some aren't. It just means that at least one is. It leaves open the possibility maybe they all are. Now, I've tried to explain the rationale for these associations in some detail, but the upshot of it all is very simple. We associate each of the four traditional categorical statements with a Venn diagram. For the A statement, shade subject minus predicate. For the O statement, put an X in subject minus predicate. For the E statement, shade the intersection. And for the I statement, put an X in the intersection. It's helpful to think in terms of differences in intersections rather than orientation on the page, because later we're going to introduce another set and the orientation will get moved around a bit.